Good morning. Super happy to be here. I think before Colin and I get started, we'd like to kind of set the stage a little bit, like share a little bit about our backgrounds, the university, a little bit about ourselves, and makerspaces too. So maybe let me get us going here. So hopefully you've had a little bit of time to walk around campus. I'm a big fan. I'm a big fan of our campus. I hope that you didn't have too much trouble parking. I think a lot of you have been walking around because of the parking issues. That's one of my biggest complaints about the campus, but at least walking around all the way from the medical center across the freeway down to the pier, it's a super beautiful spot. So a little bit about me, I'm a teaching professor. So my focus is in teaching. I very much enjoy teaching. I'm in the electrical and computer engineering department. I'm a huge advocate for project-based learning, makerspace courses. My research focus is more in engineering education and medical devices. There's a big conference in Montreal, American Society for Engineering Education, if you're interested in checking it out, in a few weeks. Medical device design. Here on our campus, we have 3 different hospitals. We have the VA, Scripps, and the Jacobs Medical Center. And there's tons of medical doctors with lots of problems. So it's a lot of fun just like working with them on different activities, solving different problems for them and for their patients. So it's a really good community that I think a lot of our making experiences kind of get into, and it's fun. I also spend some time in service. So that's kind of the teaching professor role. So teaching the focus, a little research, and then service. We have on-campus service, but I also spend a lot of time with community colleges close by and high schools, and we have a good alumni network too. So just a little bit about me there. But our school, our Jacobs School of Engineering, that's where you're at right now. And here's just a few of the buildings that we have. A ton of buildings, a ton of people in them. This building that we're in actually right now didn't make the cut of some of these. A lot of these are new, updated, kind of good spot. We have 6 different engineering departments, so they're spread across all these different buildings. Although we have these different departments, I think it's kind of interesting that we have a lot of electrical engineers that are in the bioengineering department. We have a lot of bioengineers that are in the structural engineering department. We have a lot of structural engineers in the aerospace department, right? So even though it's there, it kind of helps mostly with our students, kind of guiding them through in a different department, giving some themes. Let me give a few more numbers on our school. We have a lot of faculty. So we have almost 300 faculty just in the Jacobs School of Engineering. In just the last 11 years, about 2/3 of them were hired. So we've been growing a lot. I'm glad to be, one of those, but I think it's nice that we have been growing a lot. It's been a pretty big impact. We have a lot of research expenditures. Naturally, this is a big research hub. Hundreds of millions of dollars each year go into research here, and a good mix. I know federal spending is a challenge at the moment, right? But 50% about come from there, and the rest, we have really good relations with industry and philanthropists in the region. So we have a good mix of support kind of driving a lot of the energy. But really driving it, naturally, we have lots of great students. This is where I spend a lot of my time, is with the students. Almost 10,000 engineering students. This is a big hub of engineering students. And I would say we actually impact more. There's a lot of cognitive scientists, math students, physics students, that are able to, we're lucky to hang out with them too in our engineering spaces as well. So, and visual artists, I should throw that out too. We got a good, strong group of them in our world too. And I think what's important about that is they're getting degrees, right? So it's so important for us to be figuring out how to prepare them to escape the school and influence and hang out with all of you folks in industry. So it is our job to figure that out and prepare them for it. So this is an important step for us to kind of figure this out with our courses. And in a moment, we'll be getting into it. But I did want to take a moment to kind of share this big initiative that started in 2016 by the then dean and also still now dean, Al Pisano. He had this big push for experiencing engineering, and we call it the E4 initiative. We say that because we want all our students to experience projects, hands-on education, not just in their senior capstone, but each of the 4 years that they are a student here, right? We want them engaging with projects and knowing what side of the soldering iron to grab and things like that. Very important, right? Not at the last quarter. So this is really been a big part of my energy. I've been able to ride this wave, and a lot of other things on campus, educational activities have kind of geared up because of this. A lot of time, energy, money has gone into this world with our partners and makerspaces. So one of those makerspaces is actually down here. I spent a lot of time here. It's a nice makerspace and teaching facility. It's on the 3rd floor of the Structural and Material Engineering building. SME building. It's kind of by the trolley. If you've used the trolley, you could even just probably walk up there. We have a pretty public campus, so it's a good spot. And in this spot, I've been very fortunate to work with some great students, talented, ambitious, caring, project-focused students who are building, making, breaking things all day, every day in there. And the director of that spot, super talented. I've been lucky to work with him on my classes, and many other instructors work with him on theirs. He is Dr. Colin Zyskowski. So I'd like him to come up and share a little bit about his energy in this space and spot. So maybe we give him a nice round of applause, too.
Thanks, Karcher. Hello, everybody. My name is Colin, and I am the director of the Envision Arts and Engineering Maker Studio here at UCSD. I am not actually, as was mentioned previously, a professor. So I do, no, it's all right. But, figured I should make that clarification. I do engage in a little bit of teaching. Thanks to Karcher, we have engaged in some sort of extracurricular projects that involve PCB design and circuit board building, things like that, that I'll get into in a little bit. But yeah, I guess today I'm going to talk very briefly about 3 specific topics. First is Envision and what we do there, the kind of makeup of the space and whatnot. Second, I'm going to talk about a project that Karcher and I have been working on for the past couple of years, I guess, and is now sort of wonderfully coming to fruition. And that is the Envision Tools for Imagination boards. So that's topic number 2. And then third, I just want to give a brief shout out to Kicad and the open source community and how it's benefited our students. So yeah, a little bit about me. As I said, I am the director of Envision Maker Studio. My primary task there is to support the student staff. So we have a couple members of our esteemed staff and community present today. Thanks for coming. And really, I am there to support and enable the students and the culture that I guess we hope that thrives in Envision. We are, well, actually, I'll get into that in a moment, but my specific interests lie mostly with PCB design. So my background is actually in the arts. I have a bachelor's in English literature. I have a master's in media arts, and I have a PhD in music. All of which make me really good at designing circuit boards. So I'll talk about how I got there a little bit at the end of the talk. But I'm really interested, of course, in digital music and designing controllers and digital instruments. Engineering education is, of course, not just engineering, but arts education as well, is really important to me. And then just studying interactivity, how humans interact with machines and computers. That's something that I really find fascinating, and it's largely what my dissertation was on, networked robotics and sound source localization. But yeah, I also really love just dealing and hanging out with and working with students. And I tried to do as much of that as possible through supporting student orgs and working with individual students on personal projects and things like that. So now a bit about Envision. We are a makerspace on campus. We're one of several. We're not the biggest, we're not the fanciest, but we are definitely the hippest, as you can tell. But yeah, we are sort of half engineering and half visual arts focused. We have a lot of resources to support both of those pursuits. So we are a crucial part of the E4 initiative that Karcher talked about earlier. So we were one of the first concrete steps towards realizing that goal. And we opened up in 2016 as your basic makerspace with things like 3D printers, laser cutters. We have some woodworking tools. We have, I just remembered that I have notes. So we have some basic woodworking tools. We have a CNC router. We have resin printers, all of that kind of stuff. We have a whole craft area that is, not used for any classes necessarily, but gets a ton of use for personal projects. All told, we have 5,627 square feet of makerspace and classroom. And while we are extremely engineering-centric, we have a large focus on visual arts, we're getting more music students involved in the space now. We have a lot of cognitive scientists who come in. We really have students from all over campus who use the space. A lot of it is for classroom use, but we're really proud that tons of students come in just to use things for personal projects and to make things that they think are just fun and cool. And we try to support that as much as possible. We have a really incredible large community of makers, designers, artists, engineers. This is students, this is staff, this is faculty. There's just a great variety of people who hang out in the makerspace and who are just interested in seeing what other people are making, what other people are interested in. It's how I, just by interacting with students and other faculty, it's how I, think I stay on top of things, even if I'm a couple decades behind. But yeah, we just, as you can see, have really amazing people. Hey, I know that person. You can see Karcher. He is available, by the way, for private violin lessons if anybody is interested. Yeah, so it's just a really awesome space. You are welcome, if you have time this afternoon to come by and just walk through the space. It's not huge, it's not fancy, but it's pretty cool. Yeah, quickly, I'd like to say one last thing about Envision, and a very important thing, is that our primary focus, our primary purpose, our raison d'etre, is to serve as a classroom for engineering and arts classes. So one half of our studio, one half of that 5,627 square feet is actually classroom space. It is the space over there on the lower right. So it's a large space that can be all rooms combined into one large 90-seat classroom, or they can be split up into 3 individual 30-seat classrooms with nice AV hookups and all of that. So that's where the lectures happen. That's where students go to listen to people like Karcher and the other faculty tell them how to, incorporate theory and all of that. And then they go across the hall, and they have 2,700 feet of makerspace to hang out in and build in and work in. And it's a very unique spot on campus for that reason, because we have combined the classroom and the makerspace into one integrated unit. And I think it's probably one of the few rare cases of that existing anywhere. So we're very proud of it. And we're also proud of some of the projects that we've initiated, such as the Tools for Imagination, which I'm going to talk about now. That was the classroom slide. Okay, so the Envision Tools for Imagination. These are circuit boards that we have designed in-house at Envision. And they are meant to teach circuit board, PCB design and development and building. So these are meant to be as simple as possible. They are currently, the ones that we have functional right now are all based on the ESP32 microcontroller. Most of them use the S3 Mini chip. We have one that requires Bluetooth, which uses the rover, and I'll show you all the boards in a moment. But it's proven to be a great way to introduce circuits and PCBs to undergraduate education. Karcher is going to talk specifically about the application in the classroom, but I'll just go over what the boards are and what they do. So the main board that we have as part of this larger ecosystem is the S3 dev board, and it is an incredibly basic, very simple circuit board that is just meant to serve as a basic microcontroller. It, of course, has built-in Wi-Fi and Bluetooth. And it's got a very basic charging circuit on it. So if you have it plugged in via battery and plug the USB, it will automatically charge. It's got a simple power switch, 2 user buttons, 2 user LEDs, and that's it. A boot button, a reset button. Basic as that. All of the components are 0805 sized. Which makes it really easy for students to build. And Karcher is going to talk about that process, I think, in ECE 186. But so that's the main board that we have as the sort of brain of the Tools for Imagination. The next is a very simple shield that works with the S3 dev board. And that is just a VU meter. So all that we have on this board is a very basic microphone component, and then 11 LEDs. These are fairly large LEDs. And what makes it great is that you can teach students how to do SMD soldering with a soldering iron using this board, which for me was a sort of incredibly important part of the process of prototyping electronics, was just learning how to build a circuit board that had surface mount parts with a soldering iron. It's not fun necessarily. It's not easy or quick, but it is, I think, really incredibly important to know. And as college students are getting into this fast prototyping of electronics, it's incredibly useful. So that was sort of the purpose of that board. And then once it's built, they can just do, the very most basic forms of interaction with it. So the microphone listens to audio in a room, and the LEDs respond, and it's a, volume unit meter. So cool, simple projects for programming and interaction and PCB building. Then we start getting into more fun stuff like motor control. This is another shield, the motion shield that we have for the ESP32 S3 dev board. And of course, this focuses on motor control and motion sensing. So it's got two really nice dual motor drivers, 24-volt input, which is great if you want a car to go really fast or a quadcopter to fly really high. It's got 6-volt servo power. You can see the 3x8 grid there of through-hole components, and that is for servo connection. And then we've got the motor driver outputs at the bottom there. Those are, you can hook up, 2-stepper motors, 4 DC motors, up to 8 servos. So very fun, useful board for doing any sort of autonomous vehicle stuff or obstacle avoiding robots or maybe line following robots. But it also has a really nice IMU on it. It's got the BNO 086 motion sensor, which has the accelerometer, gyroscope, and magnetometer. And is super functional and great for students to use for any sort of entry robotics projects. Next, we have the sensor shield. This one is kind of still in development, but getting close to where we want it, and we'll have some students working on it over the summer. Wink, wink, nudge, nudge. It's great for getting students into interactivity, really sensing a ton of different stuff, but it's got the APDS 9960, which is a pretty cool gesture sensor and color sensor. It's got another less expensive IMU on it. It's got the I2S microphone. It's got an IR sensor, the RGB LED for visual output, a couple user buttons. It's really just a great tool for programming interaction and coming up with, interactive projects. Lastly, we've got the BLAMP, which obviously stands for Bluetooth Amplifier. And this is a project using the ESP32 rover, which is required because it is full Bluetooth capable. And this is a project that we designed for students to start working with some basic audio programming. And also some design beyond just the circuit board. So Karcher and I worked on another project where we taught a program called the Paths program, which is for underrepresented students who want to get into STEM. And so the project that we came up with was to have them build a Bluetooth speaker. So they actually build this circuit board themselves. Again, this board uses only 0805 components and larger. And we can use this to teach students who have never even seen a circuit board before how to build the circuit board. We have, cog-sci students, math majors come in and build this circuit board and then create their own Bluetooth speakers. It's proven to be a lot of fun. Students seem to really enjoy it. They walk away from the course with their own custom Bluetooth speaker, which they can, they also learn a little bit of CAD maybe, or, 3D design, and maybe even some woodworking. It's a really fun, all-around project. Those are the current tools for imagination that we have in our toolbox at the moment. And Karcher is going to, of course, talk more about how he uses them in the classroom and the types of projects that students are doing with them. But just wanted to give you some background on what they are. And that's about it on the tools for imagination. Lastly, I just wanted to say a word about Kicad and open source philosophy, and just how important it is. First, I mean, to everyone, but how important it was to me personally. And so, as I mentioned, I have a lot of background in music and the arts. I have zero formal training as an engineer, but because of programs like Kicad and because of people who believe in sharing and in open source philosophies, it was possible for me to, after I was 30 years old, which is when I went to grad school, it was possible for me to get into circuit board design and to start working with PCBs and electronics. And I was able to, I had never even, I think, seen a schematic until I was 34. I'm 47 now, by the way, to give a little bit of context. But yeah, I was able to do it because, people share and people are okay with not having everything be proprietary. And that, of course, had an immense impact on my life. We're fortunate, as we are in universities and taking college courses, that this stuff that we can afford to do that sort of thing. But there are a lot of people out there who can't. And, the openness and availability of programs like Kicad and things like GitHub, they're just incredible. And we should do as much as we can to support them. And I want to say, thanks to Kicad for putting on this conference and for having us speak here, because it's really awesome and, helps to get out that open source vibe and support it. So thanks.
All right. Thanks, Colin. Thanks, Colin, for all you've done and all you do still. Yeah, it is a fun environment to be in, and it is cool to see all these students engage in such a way. Yesterday, I had a couple good conversations, and it got brought up that, this ECE thing, what is ECE anymore? I think it's interesting, right? We have a lot of students graduating with the electrical engineering degree, and they're all over the place. It is great. We have so many different depths and areas that students could delve into. Maybe I'll just go back. I love asking this question in my class. In both of my classes on the project end, the beginning and the end, and I'll talk about those in a second. But it's an important question because I think if I went to ask all our different faculty, we have over 60 in the ECE department, I'd get over 60 answers to what ECE is. And I like that, right? I mean, there is no right thing. We may be leaning after the last few years a little bit more on the machine learning end of things, but that's nice too, right? We're getting pushed and pulled as the years go by, and I am fortunate to be a part of that push and pull, and Colin too. We have so many different depths and areas. It is tough to define. When I ask students to define it to their peers and explain it, I expect that this changes over the years, right? It's our job to influence every faculty, every peer is going to influence in all these different ways. Let me get to this. Since that E4 initiative, the EC department really has pushed. These are a few of the hands-on classes. I just put pictures there, but they're building pinball machines. They're working with LabVIEW and makerspace projects, building like Ferris wheels and all this stuff, autonomous cars and vehicles, working on both the front and back end of all these different. We have art of product design, rapid prototyping. EC5 and 196 is where I wanted to focus a little bit more time on. And EC5, we do have a poster out here if you want me to delve in any more on these classes. I know there's a lot of weeds to get into, but this class I've been super happy to be a part of and grow. and influence in different ways. But the idea is we're trying to explore all those different depths. There's so many different ones. We try to make some sense by having a series of, we call them labs, but they're really projects that they work on. There's a lab 0 too, where it's just intro to microcontrollers. You actually see some up there. Those are the Arduino Megas. We've just switched over. Colin has talked about it, but this last quarter they were all using the Tools for Imagination boards, and it's been really nice making that making that switch over for the students in the class. But again, they go through a series of labs. So you can see us covering communication theory. That's big here. We have, Qualcomm. Erwin Jacobs was an EC faculty, and obviously he started Qualcomm and is a huge philanthropist in the area. So our school has benefited greatly from him. So it's nice to actually start. We have a lot of faculty in the information theory and communication area. So it's good to kind of talk a little bit about the theory in the lecture, but get into that maker space and actually build some things related to it. Lab 2, they start with some like high pass, low pass filters using O-scopes, virtual benches. We were using the NI virtual benches, so it's easy to use in the maker space. But they end with building their own speaker, and it's not just following a diagram. They actually start to understand, how these high pass filters and low pass filters influence their build there. And then, being hardware for a little while, we turn a little software. We use MATLAB or Python, depending on the quarter, where they dig into signals, right? Digital signals this time. So we could see 1D and 2D signals and do some image processing, and that's pretty nice. And we end the 10-week quarter, super fast-paced class in this spot. We end it with a robot. So they learn some controls, some PID. They get to build it. They get to integrate some of the things they've learned, some soldering, 3D printing, and all these things. And they end the quarter with a competition. So I think they like the idea of not having a final exam. They put a lot of energy into that project, but they soon learn that projects take a lot more time and energy, but are rewarding in so many different ways. So just in that Maker Studio, just in this class, it's 300 students. There's, 20 classes in there, Colin, or so, something like that. You think of how many students are being pumped through this maker space, but I'm glad we require it, right? It's a good requirement to include, and that's, again, what the initiative has been doing in so many ways. I just wanted to pull up a couple things, give a couple of shout outs here too. To Anurag, he was a Project in a Box. That's a student organization on our campus. We have phenomenal student org energy on our campus. Project in a Box, PIB, he created one of these for our class. And we actually had 2 students showing off some of their new designs that we're going to influence for next year that were all built in Kicad. And they designed these out. And what's cool is they don't just design them and then they're done with them. Hundreds of students have now used this to learn how to solder. So there's a nice little area on the top, a little soldering playground to do their first header pins ever, maybe a resistor and a jumper wire or something like that. And then they go slowly through this build and get to solder these parts and get to see this work. So it's a really good way to, Anurag is now a master's student, but when he did this, it was an undergrad, and for him to work on the design skills and influence such a great group. So that's just an example of, learning to solder in the class. It can be fun when we use these PCBs. KiCad, I want to zero in a little bit more on Lab 2 there. So before Lab 2, we have a workshop that's focused on KiCad. So students will go through, they'll watch a few videos, we'll do an in-class walkthrough. And then what I like is they get to see this kind of workflow a little bit. Again, we're covering a lot of things in class, so it's hard to get into too many details, but I think it's motivating. Going through, for them, if they just saw that schematic, that's crazy, right? You can imagine your first year, you're 18 years old, digging into this for the first time. But they build it out on a breadboard. They test it with a function generator and O-scope. They see the signals flowing through. They're learning what hertz are, right? And to be able to see that and hear it is wonderful, and go from a breadboard to those perf boards. Reed had a great presentation yesterday. He was sharing how difficult that process is, right? So just being able to engage and struggle there, but to take it further. Before COVID, we required it. Since we've made it an extra credit assignment just because of timing, but we'll see if we could get it on board. But extra credit is they would design in Kicad, or designing in Kicad was a requirement for this circuit just to practice Kicad a little bit more. But if they wanted to actually go through, pre-COVID, we used OshPart codes. They gave us all these codes and we were able to order through them. So the students would go on there, put their PCB and order it. And it'd be, again, just to do that in a few weeks. Pretty amazing experience. in my view, that I certainly did not have when I was an undergrad. So I guess just one quick thing is there's all these other classes, right? UCSD prides ourselves in theory. I'm probably going to go a couple minutes into the coffee break, Seth. I hope that's okay. I'm sorry, everyone. I guess you could just leave if you're bored. But thanks. Yeah. Sorry about that. But no, I just like to share a little bit more. But our school prides ourselves in theory. We're very good at the math and the physics, right? That's so important. But we have found that these classes can complement. In this case, EC5 kind of brings this up. We start saying, hey, if you really like this lab too, you should check out some of these classes. A couple of them are required, but most of them, we have so many different classes that they could go in that depth and that direction and strengthen those skills. And I think that's really nice that we have all these different faculty able to teach these different areas. But one thing on the other end, so now after they've taken all these classes, they have these different depths from left to right. I have this 196 course that we've been able to kind of reinvigorate, redesign over the years. This is the course description. I kind of just put that there. But for time, I'll just jump to what I tell the students the class is more about. And I like to say that they should build an awesome. I like the word relevant. I don't get overly excited about novel. I think having a relevant project in this class is really nice. Hands-on project, of course. That they work on a team. That there's pros and cons of that, right? It's challenging to work on a team, but very rewarding. They work on teams of 3. They get to work on technical skills, and they really get to think about. A lot of them are going to be entering the job market in the next year or so. They should be working on a project that really that they could put on their resume, right? Those things are important. They could bring the skills that they've had. So this is a senior design class, and the design method that I like to share with them and force upon them in a way is the double diamond of design. I think engineers love solutions, right? We really like solving problems, but sometimes we forget about the problem part. So I like that there's a little bit of a focus when I bring this up on really understanding a problem well when you're going through the design process, at that high level. We are trying to cram this into 10 weeks, so a little difficult. So we kind of looks more like this, just because we do like solutions a lot. So I think it's very much worth the 2 weeks, but just giving you kind of an idea that these teams, they form in the first 3 weeks. We explore problems or in the first 2 weeks, and then they have to define that problem very well before they could really venture off into solving it. So the way we kind of set this up, I've tried to keep this timeline to help us. But you can kind of see we have these mini projects. This is where the tools for imagination really come in. And then we have the final project. They're thinking about the final project from the beginning with the problem, but really we get their skills kind of worked up in the first few weeks. And I'll zero in on the VU meter. That's what Colin shared a moment ago. And again, if you want to check out the booth a little later, I could show you some of these examples. But just starting with the light shield, we actually, day 1 is not a syllabus day, right? We don't just sit there and talk about the syllabus. They actually get these these printed circuit boards, and they have to hand solder this. So they are SMD components there, but for many of them, some of them don't actually come from a pure EE or have taken EC5. So for some of them, just getting soldering again going is good. But I love that they see that on day 1. Then day 2, what Colin was sharing, he actually comes in and gives a demo on day 2, and they build out, they assemble that dev board. So in EC5 we use the dev board, we don't assemble it, we actually get them assembled for the class, but then in this class they actually assemble it. In those 2 days, it's a little challenging to go through that. We're improving on how many people get the first one right, but even just getting the solder paste on and having that experience to get intimate with those 0805 components, being able to get a feel for that is huge, because what we learned in the class, this kind of almost flipped approach to PCB design, this is super valuable. If you just start with Kicad and going for the circuit, they're not yet thinking of these things in the layout. So we really love on the first week this just being super aggressive and fun, and giving them some deadlines, engaging with the makerspace. And so I think once they get the board plugged in, we do a little circuit Python for this. Instead of C, we do have some tutorials in C for the spinning and blinking part, motors and GUI that I won't talk about here. But I like, again, the kind of aggressiveness here that we start with the class, that the students are just diving in deep immediately into these PCBs. So going back to the final project, Almost through. A few more slides. Thanks, everyone. So going back to this final project deal, let me kind of jump here, is week 3, we actually do a KiCad, more so KiCad tutorial. We have some videos, but we do a walkthrough in class to kind of show them where the B button is and, all these things to walk them through. They get a feel for that, but then in week 4, they really have a good idea of what they need to do for their problem. For solving their problem. This motivates them solidifying it more. I mean, we only have 10 weeks and they need to order parts. We have 17 this quarter, 17 different projects going on, very different problems. So they're all kind of figuring out what sensors, what actuators. When they're designing their PCB, that plays the huge role, right? Which microcontroller are they even going to use? All these things come into play. They're thinking about it in week 4 and week 5. They have peer-to-peer evaluations. We have some phenomenal instructional assistants that are here that know KiCad way better than I do for sure, and they're able to help all the students kind of iterate on their designs. At the end of week 5, halfway through, we submit this to get them manufactured, fabbed, and sent back to us. So we usually get them in week 7 sometime. That turnaround needs to be quick because of the quarter system, but I'm glad logistically I think we figured it out. I think it's a challenging experience for the students and even just the ordering experience, but it's working really well in our class. I was able to take Andrew, who's from Portland State, who's somewhere in here. He walked over yesterday and checked this out. I wasn't going to show a week 9 picture because usually that's when students are especially stressed and worried about their project. But there were a few in there right then showing them the PCB, kind of working through it. Pretty cool setup. So that was in the Maker Studio yesterday. And then you hope you have some happy students at the end. They are. The experience is definitely a learning experience, and they get to show off their work with a big demo day at the end. And that demo day, we have these posters. They get to show off how they solved that problem and actually demo it, talk about their different designs. And me trying to go a little quicker is zooming into one of those posters. You can see what they're showing off, right? This is where they've been able to go through this PCB design assembly workflow themselves. They get these stencils themselves and put it all together. They figure out how to solve that problem with these integrated PCBs. And maybe I'll just share here too that, I think here is that this is a great part for ECE. Maybe I could just say here, I wanted to go back to this, what is ECE? Students are all over the place. And actually the PCB is just a great spot to ground the students, whether they're software or hardware. Sometimes the teams will lean one way or the other, but this PCB, the microcontroller, the embedded system, this is where that rubber meets the road, right? They're able to actually connect with one another and maybe veer a little left or right depending on their interests. But I really like that has kind of kept the teams together. They work on it together, but they may shoot again more in the software or maybe even the back end side of things and have a lot of energy there, or maybe more hardware. And maybe they don't even have a microcontroller, right? Maybe they just want to be very much on the hardware end of things. And that still works for there. Maybe I'll just say that what is ECE? It's going to be changing. It's always going to be changing. I think there is certainly a place in our educational system to help them kind of define and work on teams. This makerspace initiative, this engineering, exploring engineering initiative, being able to experience it is a huge deal, right? And we love theory, we love math, and we know it could actually be a lot better when we have these projects kind of complementing it in different ways. So I will allow everyone to leave in a moment, in one moment, but I was really gearing up for some feedback. I wasn't sure where we'd land on time, and I have been so fortunate to be able to talk with you today, with you yesterday, and I hope we could continue those conversations. I think for us, Colin kind of shared that we just kind of started integrating this. It's an iterative process. We're still learning on how to do this well, how to do this better. We're very glad it's happening. It's impacting hundreds and hundreds of students, not just in ECE, across a lot of those Envision Maker Studio classes, and I expect it to continue to influence many classes across the nation. So I look forward to being a part of that. I'll add just another picture. That's always good. I did want to make sure, again, Colin did a good job too, but that we do say thank you maybe I'll start here. we have a lot of phenomenal instructional assistants. I did want to take a moment for these two. I don't know if we would have so aggressively pushed this coming out of COVID if it wasn't for their talents. They are fortunately or unfortunately in industry now, doing super well, but their extra energy. I mean, we have unions, so they definitely did not work extra, but they cared so much, right, about this class and this mission. I'd like to say it was from the top down, me and Colin. It wasn't. The students want to do this. We have so much energy to engage with this type of this community PCB design in the classroom, and they were the ones who were pushing KiCad even more than us, right? And I think that was huge. And I will say, though, for sure, KiCad. This community is huge. Access is the biggest thing in education. We need students to have access. They can't, I mean, just to pick on the Mac thing, right? When half of our students have Macs, I'm glad they do, but they need to have access in that way. There's students in so many different groups. They want to go home and work on this. They want to be able to download all their computers. They want to be able to use it after school. They don't want to wait. If they graduate, they don't want to have to figure out how to switch. Being able to use KiCad has been a fuel for our community, and I think it's, again, going to be a fuel for many others. I'd very much like to thank Seth for setting this up and making this happen. Seth, thank you very much for inviting us and letting us be a part of this. Yeah, he deserves certainly a round of applause. And I know, Seth, I know you represent the whole KiCad community, and you work so well with them. It's been so nice engaging with you. I hope to continue that. I hope we can continue to grow as a community and impact so many students in the future. So, again, thank you so much for a great 2 days here, or 3 days, and I hope for many more days in the future. Thanks, everyone. Oh, there's questions. I forgot. I was hoping you guys could get to coffee. Of
Well,
course,
yeah, you can leave. Well,
there's
I
the
could
coffee break.
I could probably speak with both
Yeah.
of you.
No, thank you. I appreciate
for about
the questions.
8 hours. So I had the opportunity to kind of be a rogue professor at Penn State. I had a appointment at a research lab, but when the research professors didn't want to teach the hands-on, they would find people in the engineers in the lab to do it. But I really appreciate somewhat flipping the traditional model of getting hands-on early, because at Penn State, it's like your traditional 2 years. You haven't actually seen anything yet. But so I had the opportunity to kind of like go rogue, and like one of my first experiences was EE300 was like, devices, diodes, transistors, and they were the type of classes too where you might have 300 students across in a big room, and you had to follow a curriculum. But the one thing, and I didn't realize the impact on it because some of these students were computer engineering, is you start with a diode, right? There's diode, the physics, there's diode, the PN junction, there's diode, the schematic drawing. And I realized, and there's diode, like the small signal model, that I went back to the lab and I found every diode, big, small, whatever, put on a piece of cardboard and passed it around and said, these are all diodes. And that had like an incredible effect, because that was the first time there was a visceral, tangible feeling that like connecting this model, which really isn't reality, it's like some perception of it, to the real thing. And that like went really far, especially in like a blend where it's like some comp eng and some like electrical. But the other experience I found out I had, kind of going rogue a little bit, I taught an FPGA course.
Redirect you to the question.
Yeah. Well, I should say,
Thank you for sharing.
I just want to give you positive feedback, is
I
that
appreciate
the
it.
project-based learning, but I found that testing through projects is such a good thing. Like we didn't do midterms and finals, we did project presentations and proposals. Flipping testing based upon what you're interested in implementing was huge. So I just want to
thank
give
you.
positive feedback. I love the approach.
No, thank
So-
you. I'd like to give you feedback on your feedback.
yeah, okay. But keep doing it. It's just, don't stop. And if anyone gives you flack, just tell them someone from PA said keep going.
Oh, I appreciate it. My comment on that, though, thank you so much for sharing, is that we're fortunate in education. We get to see those experiences daily, right? These students are using these projects in their interviews, and they come back to us and share with us the similar things, right? How valuable these experiences are. So I think we're lucky to hear this type of feedback commonly. I think if you haven't worked too much in the education space, check it out. Maybe even hang out with us every once in a while if you'd be willing. We have so many eager students wanting to hear your stories too about your transition into industry and impact that it would really make a big difference for them hearing that early. They are engaging with these projects, and we're trying to do that better. So again, I appreciate the feedback, and I hope Colin and I and all the students here, I hope we could have a lot more of it. So thank you again for that. Thanks. Another question, thanks. Thank you.
I was just curious, as the students are kind of learning electronics and picking up KiCad for the first time, what do you think has been the hardest thing for them to learn? Or the hardest thing to overcome in that process?
Yeah, I'd like to thank Graham, again, for documentation related things. That's an important aspect of it. I think what has happened in the last few years has been more of me having difficulties supporting. I think we have such a good group of instructional assistants. In the first class, EC5, it's getting them comfortable with just raising their hand and asking. I think most of the level of questions have been very straightforward. It's in 196 that the diversity really comes out. That their projects are just so all over the place and needing different things. I just had a talk with another Graham about things that I didn't even understand related to MLCC capacitors changing and their capacitance dependent on voltage. And maybe I see some people nodding their heads. I don't know much about that, right? And for me, there's so many little things that start to pop up that are important for us to figure out. And I think this is where again, more feedback if we had time or later when we have chances to talk, what are some of the things we should really be highlighting early? I think the hardest thing for me has been on the logistical side, being able to make sure the students are able to submit this as soon as possible with good reviews. Of course, the assembler will be able to get some feedback to us and we can make some change there, but that also delays the parts coming back to us. And if it delays even a week, sometimes it has, how do you kind of make that still, them be able to have a positive engineering experience and ensure it is a success, and however we want to define that, that could be a little bit more challenging for me. But I think at the low level, we've been grateful for a lot of documentation has changed recently. So I think that's been kind of a big play. I would say one last thing is one of our IAs, JPAC, made some really nice videos that our EC5 students have been using a lot, and that has changed it. We do they do a pre-lab videos where they learn kind of step by step. They go through it with him, and then they come into class and we do it together as a class. So having kind of multimodal experiential learning is helpful. But yeah, thanks for the question too. Great.
Hi. Wait, can you hear me? Yeah, okay. Sorry. So I'm from Cal Poly Pomona. I'm in my starting my fourth year, and we're running from our, research lab / club, Bronco Space. And we have a program called Blade where students basically make CubeSats for about 8 months. They do the whole design process. And I'm kind of wondering from an E perspective, if there's a freshman or somebody who has not learned anything about PCB design and is starting completely from scratch, what is kind of your design process or your curriculum process to kind of getting students on board with the idea of actually producing one and being comfortable with that? Because I feel like this year and even last year when I participated in this program, first as a student and then secondly actually running the program, so many students are incredibly reluctant to even start or consider the idea because it seems so overwhelming. What would you recommend as to what are the key steps towards getting them ready to start to actually make something on their own?
Wow, wonderful. Thank you for the question. And 99.999% of students coming in have not built and assembled their own PCB, right? So it's a super common thing. And there's that reluctance that you spoke to really nicely. That's super common. And not everyone built their own radio coming into EC. A lot of students chose EC because they're good at math, they're good at physics. Maybe they had a mentor that kind of pushed them in that direction. It's not always the build a radio moment, and we're glad to give it to them. Them being empowered of being able just to plug in a jumper wire on day one I know it sounds kind of basic maybe to many of us, we're blinking an LED, but when they blink an LED, and they did that themselves, they knew that line of code, they changed it, they wrote that code that made it blink faster, they figured out that the diode, the LED needed to be flipped over. Those things are huge and help with that reluctance. When it comes to PCB design, I think in EC5, we're just happy we do it. I think instructors maybe should have a lower bar if they're in those first year classes. Don't feel like you need to have this whole PCB design curriculum. I feel like here, of course, there's a lot of energy and I'm sure criticisms on my approach and technique. And if you looked, at the details, maybe there'd be way more criticisms. But I think the idea, I'm super happy it happens. And I think the students are too, just being forced, to overcome that and plug in that jumper wire or open up KiCad just to download it, to look at a document themselves and try to look at a schematic and turn it into a schematic file and then a board file, and being able to go through that is huge. And it is really rewarding when we can follow up with that actual build, when you get that in your hands and you see even the difference. Because breadboards too, we're dealing with audio signals. It's sometimes a little rough. You have all these wires are kind of circled together. Then you get on the PCB, or actually the soldering, it already helps, right? Going from that step, the prototyping with soldering helps. It's a better, more reliable board. It sounds better. And then you get to the PCB and it's a whole nother level. So them going through that progression, it is challenging to fit into a classroom experience. That's why I was kind of talking a lot about time and depths, because there's so many different interests. But I do think every student should just have a chance to try it out and be forced to try it out, I guess. And then they get to pick. If they want to go more towards software, machine learning, DSP, there are tons of opportunities there, and that's great. But sometimes even they find out 10 years from now that, wow, they're happy that they did do that 10 years ago, and now they're getting back into it, and KiCad will still be there, right? So that's good. Happy about that. Seth talked about the bus factor yesterday. So.